Today we're going to redo an example that I started last time. And I made a mistake at the very end, so we're going to do it again. So it's going to be a Taylor series. Example. And maybe I'll do two, just so that we make it worthwhile re-recording the video. So we're going to start with the same function. And we have the function being f of x equals sine of x at a equals pi over 2. That's going to be the center of our Taylor series. Remember, the formula for the Taylor series that we're after is going to be the sum from n equals to 0 to infinity of a Cn that is of the form nth derivative evaluated at a over n factorial times x minus a to the n. Okay? So now that right there, that's what we're after. A in this case is going to be pi over 2. And so what we need to do is take all the derivatives of sine. So we will start with the 0 derivative and we'll move our way up. Alright. So let's start with the 0 derivative, which is just f evaluated at pi over 2. In this case, sine at pi over 2 is 1. Now we go to our first derivative. That's going to be the derivative of the sine, which is the cosine of x, evaluated at pi over 2. But we know that that is 0. Alright, let's move to the next one. How about we take this second derivative at pi over 2. That would be the derivative of the cosine, not at pi over 2, but cosine of x, which is going to be negative sine, and I'm going to evaluate that at pi over 2, which is going to be negative 1. Let's put it down here. Negative 1. Alright, so third derivative. By the fourth derivative, you normally see the pattern. And the reason is going to be because I started with the sine, I'm at negative sine. So my next derivative is going to be derivative of the negative sine is going to be the negative cosine at pi over 2, which is going to be 0. And by the fourth derivative, as I said, we will probably have the pattern down. I'm going to evaluate it at pi over 2. And that is going to be the derivative of the negative cosine, which is the sine. At pi over 2, let's put it down here in case I'm running out of space. I think I still have a little bit of space, but let's leave it there. Alright, so now, why am I saying that now I should be able to see the pattern? Let's write that. Is because you see, I'm back to the sine of x. And that's where I started. So whenever I take my next derivative, so you see, f0 was sine. f4, the fourth derivative, is sine. So the fifth derivative is going to be the same as the first derivative. So I want to go back to a 0. Then the sixth derivative will be the same as a 2. So back to a negative 1. So what that tells me is, I should use the other color, that the nth derivative is going to be, so at pi over 2, is going to be equal to, well, it's going to be equal to different things. 0 if n is odd. I don't think odd will fit. Maybe. And it's going to be negative 1 to the, well, you see, negative 1 to the 0 is 1. Then you have negative 1 to the 2 should be 1, so it's going to be really negative 1 to the n over 2. Because if it's n is equal to 0, you get positive 1. If you have n equals to 2, you get 2 over 2, you get negative 1. And then n equals to 4, you get 4 over 2, negative 1 squared is 1. And then in this case, if n is even. I don't think I can fit that. I'll put it down here. Hopefully it fits. No, I'm out of screen. Well, if n is even. So now we're going to try to put that together into this sum right here. So let me erase this. I'm going to leave this here as a cheat sheet, and I'm going to try to put it here. All right. All right, so we copied this right here. So if we try to plug that into what we have here, f of x should be equal to the sum from n equals 0 to infinity. And then I'm going to have this expression here. But you see, what I should be doing is changing my n and writing it as 2k. Because that's going to take all the values where n is even. So if I do that, this -1, well, technically I won't have to change this one for a k. And that's what I didn't do last time. I did it too quickly. And I should have done it this way so it makes more sense. So I'm going to have -1 to the k. That's going to be that n over 2. In fact, I can write it here. N over 2, when you divide it by 2 on both sides, it gives you k. And that's going to be the value we're going to be using. And now, down here, I'm going to have n factorial, but now I'm counting over k. So I'm going to write 2k instead of n factorial. So that is going to take care of that one. And then I'm going to have x minus pi over 2. Barely going to have room to the 2k. Does the 2k fit? Whew, it's going to be tight. So now, what I have to figure out is what's going to be the radius and the interval of convergence. So to do that, you're going to compute your radius of convergence. Well, no, firstly, you're going to do your ratio test. So you're going to do limit as n goes to infinity of, and you're going to grab this term without the -1 to the k because, well, you're going to do absolute value. So you can ignore that. The rest of the terms you can just write as absolute value of x minus pi over 2 to the power of 2 to the k or times k plus 1, that's the k plus 1 term, over 2 times k plus 1, the whole thing factorial. Now I'm going to multiply times the reciprocal of this term, so an absolute value as well. So absolute value of x minus pi over 2 to the 2k. My monitor looks like it still fits. Hopefully it does. And then here 2k factorial. Alright, so things that do cancel. So when I cancel this 2k, this is 2k plus 2. So I cancel a 2k of that, and so the exponent is going to be a 2 there. That was no problem. So that's going to be the limit as n goes to infinity. And now I'm going to have x minus pi over 2 to the 2k, to the 2, sorry, that's the one that's left over. And now to figure out what's left over here, what I'm going to do, I'm going to copy my 2k factorial here. Now this one right here, I'm going to work with is 2k plus 2 when I distribute. So I'm going to get the 2k plus 2. 1 less is 2k plus 1. And then I'm going to have 2k. But when I get to 2k, throw in your factorial. Because at that point, you have something to cancel with. You see, I start going down until I got to the one that matched. And I was able to cancel it. Now, notice that it doesn't matter what the value of the x minus pi over 2 is. This right here, oh, I'm so used to using k. You see that I use n here. So all these limits should be k. I mean, yeah. I mean, you sure could take the substitution back and write this as n plus 2 over n plus 1, but no, it doesn't work that way. So at this point, then, you just take your limit, and this gives you 0. No matter what this is, that tells you that the radius of convergence is infinite, and therefore the series converges everywhere. Alright, and that's gonna do it. And hopefully this time the video is not blurry, the math is right, and I can upload a much better video than the one we did before. So thank you for watching. Sorry about that mess. And I hope you follow me or you join me for the next video So until next time, thank you for watching.